Thank you, Hugh, very much. I'm delighted to have this opportunity to speak to a rather large and broad audience on aspects of our chemical work at Princeton. I want to begin by expressing our gratitude for the Center for having truly a pervasive impact on the way we look at problems in chemical synthesis. And in recent times, my lab has been rather active developing various catalytic hydrogen atom transfer reactions, but I've decided not to talk about that work today, but rather in 20 minutes pursue the theme of CH functionalization as enabling transformations in natural product synthesis. And after thinking about how to do this, and after having a few discussions with you, I've decided to address some truly historically significant achievements in synthesis, and then sort of sprinkle into that some of the work from my own lab. Now, actually, it's difficult for me to follow in the wake of the last two lectures, which were both really fantastic. And we've already heard some really beautiful examples of CH functionalizations in natural product synthesis. So I'll show you a few more, but next slide, please. But first, I want to begin by acknowledging an achievement in organic synthesis that never intended to use CH functionalization, and I'm referring to the synthesis of tropanone by Robert Robinson. This was described 100 years ago, so this is the 100th anniversary of this historically significant and influential achievement in synthesis. Next slide. Many of the chemists who are attending know this work well. It is rightly viewed as a paragon for nature-inspired synthesis. It has been called a solitary forerunner of the modern era of organic natural product synthesis, and it offers a rather beautiful example of a spontaneous covalent self-assembly from three rather simple organic compounds. And as you can see, this is an achievement that was what you could call rather dependent on the activating effects of organic functional groups. So that was described in 1917. Next slide, please. But there was an example of some CH functionalizations that were described. These were described significantly earlier. And I'm referring specifically to the work of Hofmann, also Leffler and Freytag. This is organic chemical reactivity that was described in 1883. This is reactivity that would come to be known broadly as the Hofmann-Leffler-Freytag reaction, and a very beautiful example of this reactivity is found in a synthesis of nicotine from 1909. So well before the tropanone synthesis by Robinson, we have this rather charming synthesis of nicotine featuring this Hofmann-Leffler-Freytag reaction. And today, as we look at this reaction, we understand that it goes by way of the reactivity of a heteroatom-centered radical. These are rather aggressive reactive species that have a proclivity to steal hydrogen atoms from nearby carbons through ordered six-centered transition state arrangements. You get a heteroatom radical that generates a carbon radical in the course of a hydrogen atom transfer. The carbon radical steals a bromine atom so that the chain can propagate. And then in the last step, you just treat the reaction with base and you drive a ring-forming substitution reaction. So this was known in 1909. In 1960, next slide, please, Derek Barton, one of the great pioneers in the development of radical chemistry, looked upon a problem in steroid synthesis that loomed large in that day. And that problem is embodied by the structure of aldosterone C21 acetate. And in response to that structure, Barton conceived of a rather interesting and important reaction that bears his name. This is called the Barton nitrite ester photolysis reaction. You start with a nitrite ester, you give light energy to it, you induce homolysis of the weak NO bond. The resulting oxygen-centered radical is also capable, like nitrogen-centered radicals are, that oxygen-centered radical will steal a hydrogen atom from a totally unactivated site that generates a carbon-centered radical that combines with nitrosyl radical. A tautomerization event then gives structures having aldehyde oxidation states. This is a really beautiful example of a problem in synthesis that drove the development of a reaction that has had a lasting impact on the field of synthesis. 5 years after that, next slide, please. R.B. Woodward, an outstanding, organic chemist, of course, described in 1966. This was the subject of his Nobel lecture was their synthesis of cephalosporin. And when Woodward and his co-workers at the Woodward Institute in Basel, when they looked at cephalosporin C, they recognized the atoms of cysteine embedded in that structure. So this was a rather bold idea in the 60s. So the idea was to take cysteine and somehow morph that into cephalosporin C. But to do that, they would need to functionalize the least activated position in the cysteine molecule, which was the CH2, right? So rather challenging. Next slide. So what they did is they took cysteine and they converted cysteine into a rather rigid molecular context. They built a thiazolidine, and they discovered if you allow that thiazolidine to react with dimethyl azo dicarboxylate, you can achieve the desired CH functionalization reaction by a mechanism that had no precedent before this work. So this was totally a novel reaction, and it was discovered after a fair amount of experimentation. I think that's what Woodward said. After a fair amount of experimentation, it was discovered that the heating of the thiazolidine shown on the left with dimethyl azo dicarboxylate accomplished the needed CH functionalization reaction. And it's a beautiful reaction that could be viewed as a directed CH functionalization. You've got the polarizable sulfur atom engaging the diazo. You generate a putative ylide, and then there's a Stevens-like rearrangement to give a new carbon-nitrogen bond. So a really interesting transformation, one that has always inspired myself and my students in my lab. So the next slide. So we had this work by Woodward in mind, and also, there was a rather large collection of CH oxidation reactions. We had these reactions in mind when we started to think about jodaphenolide as an objective for synthesis. And when I say we, I mean and David Seiler. So we're looking at jodaphenolide, and we generated the somewhat bold idea that we should try to create the rightmost lactone system in the course of a CH oxidation reaction. So we would need to somehow oxidize the methyl group that I highlight in red and generate a lactone ring in the course of that chemistry. So the idea was, could we do that? Could that be the last step in the synthesis? Next slide. So we were inspired by a paper by my friend Dalibor Samish at the University of Columbia. And Samish has had a long interest in the potential of Sheloff reactivity in challenging our undertakings in synthesis. And they had already described some years ago that you can take amino acids and achieve directed oxidations of remote unactivated carbons in these compounds, and they generated, lactonic systems by directed Sheloff chemistry. So next slide. So that was our favorite idea, was that maybe this work by Dali demonstrating that Sheloff reactivity can indeed be taken into rather complex, even intricate structural contexts. We had this idea that maybe that reaction worked, but that was reaction 1 and that failed, and so did reactions 2 through 10. So nothing that we tried would allow us to achieve the desired oxidation of the methyl group. So we were sort of in trouble because David and Jeffrey made a very nice synthesis of the structure that you see. But nothing that we tried would allow us to achieve the needed CH oxidation. So you can either panic or, change your design. Fortunately for us, the way in which we synthesized the compound on the left was rather flexible. Next slide. So we could retreat to a structural context in which we could achieve the desired methyl oxidation by capitalizing on Melanie Sanford's very important variation of the Baldwin oxidation. So I'm trying. This is a rather busy slide, but I want to direct your attention to the structure in the middle on the bottom there. The structure that has the highlighted methyl group. So we would generate that kind of propellane structure. The donor group would be something like an oxime, or to be more precise, an oxime acetate. And under the conditions defined by Sanford and co-workers, we would then seek to achieve the desired directed oxidation of that methyl group. And in fact, that worked, and that was the only method that would allow us to oxidize that methyl group. So I have a soft spot in my heart for Melanie's variant of the Baldwin oxidation. Having achieved that directed oxidation, David and Jeff could make the short jump to jodophenolide. So I've shown you a few reactions so far that demonstrate the power of direct oxidations of strong unactivated carbon-hydrogen bonds. But we can also take strong unactivated carbon-hydrogen bonds and convert them directly into carbon-carbon bonds. So next slide, please. This is a key step in a rather early synthesis by Doug Tabor's lab at the University of Delaware, showing quite clearly this ability to convert CH bonds directly to CC bonds by insertions of metal stabilized carbines into unactivated CH bonds. It's a rather lovely synthesis of pentyleno lactone E methyl ester. We see two fantastic examples of CH insertion reactions in the next slide. These are key steps in the Dubois synthesis of tetrodotoxin, an outstanding achievement. Note the use of a stereospecific rhodium carbene CH insertion to achieve the making of a 6-membered ring in the tetrodotoxin structure. That molecule that's made by the CH insertion reaction is converted by a stepwise process into a carbamate that's shown in the second row right side. That structure, under the conditions shown over the arrow, is then converted into a needed intermediate having a rather crowded carbon-nitrogen bond. So this is outstanding chemistry that involves the generation of an iminoiodine, and rhodium acts on that to give a putative rhodium nitrine, and the rhodium nitrine bites into a rather crowded CH bond. And both of these reactions are really quite stunning. This is an outstanding example of a contemporary synthesis, to be sure. Next slide. I show you here a reaction that I'm also quite fond of. This is this is the cornerstone concept that underlies Hugh Davis's synthesis of, I can't pronounce it, but I think it's elisaptorosin B and coulombiosin A. Coulombiosin is pretty easy to say. The other one is not. But the concept is great, okay? So you can see that on the bottom half of the slide. So you can take, hydrocarbons and react them with donor acceptor carbines, and you can get CH insertion reactions that are attended by cope rearrangements. So it's a really interesting and non-obvious way to establish remote stereo relationships through a process that clearly has an ordered transition state. And I want to show one additional example before I show you something from my lab. So next slide. I love this work. This is work also by Dolly Samish's lab. And I actually have fond memories of a time when Dolly and I were both postdoctoral co-workers, and we were talking about the structure of resinolim, and we had this dream that maybe you could start with a symmetrical structure and achieve a directed CH functionalization. If you could somehow differentiate the enantiotopic ethyl groups in this kind of structure, that would be a really interesting and rather direct way of dealing with the resinolim problem. And indeed, that works. So in Dolly's laboratory, they found that a directed platination of one of the ethyl groups put them on a path to generating a structure having a new alkene in it. So they would break symmetry in the course of a directed Sheloff reaction. And it was the cornerstone of their rather imaginative synthesis of resinolone. I've always liked the exploitation of symmetry as a design element in this work. And in the next slide, you see an idea in which we would try to do something similar in our effort to build indoxamycin F. So indoxamycin F happens to be a rather biologically active anti-cancer natural product. It has an architecture that is sort of challenging. It doesn't scream of something that has symmetry, but we had a dream that maybe indoxamycin F could originate from a structure having symmetry. And the idea was that we might build the structure on the left and break its symmetry by site-selective CH functionalizations. And this project ended up forming the basis for a really excellent collaboration between my lab, Hugh's lab within the center, also Jinquan Yu's lab at Scripps. We all worked hard on this problem of trying to do selective chemistry, site-selective chemistry on the kind of symmetrical substrate that you see on the left. So the next slide shows a catalyst that we inherited from Hugh. So one of the great benefits of being a member in the center is that my students and I, we are often the beneficiary of new catalysts that get developed by various members of the center. We've got a lot of work going on in the area of catalyst and reaction development, and consumers like us. So Sarah called herself a consumer. We too are consumers of these reactions and these methods, and we just inherit these catalysts. We're kind of spoiled. But that's the dirodium catalyst that allowed to do the reactions that you see on the next slide. So the structures on the left, we made them in racemic form, but by way of Lotus separations technology, which operates out of the Department of Chemistry at Princeton, we could resolve the racemate, and we had access to both mirror image forms of the structures that you see on the left side. And we found with Damien Villette from Hugh's lab, he was a very important contributor to this work. Damien and Aaron Bedell and Graham Hone, they found that you can achieve site-selective intermolecular CH insertion reactions with donor-acceptor carbene. So using that dirodium catalyst that I showed you on the prior slide, we could actually generate new carbon-carbon bonds in the course of site-selective intermolecular CH insertion reactions. Now, the plus enantiomer does this chemistry very well with the S enantiomer of the catalyst. It reacts rather efficiently, gives the product that you see in the upper right and very good yield, also with a high level of diastereoselectivity. The minus enantiomer will also undergo conversion to a product having a new CC bond, but it does so less efficiently, and the diastereoselectivity is not as good. But interestingly, both of the new CC bond formations were found to take place away from the ring junction methyl groups and actually toward the alkenes that you see in the substrates on the left. So next slide. Yeah, there we go. So having defined a way in which we could achieve unions of fragments through a carbon-carbon bond, we took on the challenge of forming perhaps the most challenging aspect of the indoxamycin problem would be that six-membered ring that's fused to the 5,5 system. So the idea here was that, well, we have products with arenes in them, and we've got what you could call a relatively weak directing element in the form of an ester. And the idea was that perhaps that ester could direct a palidation of the aromatic ring, and that the intermediate organopalladium species might then undergo a spontaneous hex cyclization. So that seemed like a fine idea, but it was a really difficult idea to reduce to practice. Next slide. And Aaron and Graham had to do a lot of experimentation before they could figure out how to do this. And we benefited clearly from Jin Kuan Yu's counsel. So he gave us advice on how we might actually achieve this reaction. And after a lot of work under the conditions that are shown above and below the arrow, we can in fact achieve the directed palidation with a concomitant HEC. And we generated a few different structures by way of that type of ring formation, and we obtained one as a nice crystalline solid, and we established its stereochemistry by way of an X-ray crystallographic analysis. So this these reactions. So I'm not offering you a total synthesis of indoxamycin with this work, but I would say this is certainly one of probably the most challenging, partial synthesis that we've ever gotten involved with. It was it took us a while to make these reactions all that they could be, so to say. So on the next slide, I show you another natural product. It's Maui Crystal V. And this is a structure that has attracted a great deal of interest in the field of synthesis. A lot of groups worked on Maui Crystal V. There have been several syntheses now, the most recent one being only 11 steps from Phil Barron's lab. Rather striking. I never dreamed that one could generate Maui Crystal V in 11 or so steps. We were drawn to this problem a number of years ago, and we pursued various concepts that were interesting in certain respects. And I'm going to address only one today. Next slide. The idea here was that we would build a structure on the left from something like limonene oxide. And in fact, my students, Jillian Spangler, Michael Smith, and our former postdoc, Dr. Lawrence Herdice, in my lab at Princeton, they built that structure very nicely from limonene oxide, and it has a protecting group in it. You'll see quite clearly the ketal that I've highlighted in red. And of course, you never really want to use a protecting group in a synthesis, but we thought, well, if we have to, let's try to think of a way in which we might keep the atoms of the protecting group. So we're going to use the ketal in the traditional way as a protecting group, but in the course of the work, we're going to figure out how we can retain its atoms and have them be expressed in either the eventual Maui Crystal V or in advanced intermediates that would have key elements of Maui Crystal V. So in fact, we did build this structure on the left by a very nice synthesis. We could make gram quantities of that material. It has a ketal protecting group in it so that we could do the diazo transfer reaction shown on the next slide. So having that ketal in place, the diazo transfer was rather easily achieved. Could even be done on large scale. And we made the diazo compound, and now we're thinking about pioneering work by Tessia, by Hugh Davis, by Michael Doyle, by Doug Tabor. We want a rhodium carbene that would originate from that diazo compound to bite into a nearby CH bond. And that reaction is shown on the next slide. And that reaction was found to be uniquely successful if you use the catalyst shown over the arrow, that really interesting dirhodium paddle wheel catalyst with a cyclopropane ring in its structure. And that catalyst is readily available if you get it as a gift from Hugh Davis. Actually, no, I'm hoping some people are laughing at that. That was a little joke, but honestly, this stuff can be made by way of a very effective synthesis that's described in this Jack's paper that's cited on this slide. So you can make that. I never made that catalyst, and actually my students didn't have to make it either because we have a very close relationship with Hugh and his lab, and we often inherit these catalysts just as gifts. So he gave us this catalyst. And Hugh, I'm very happy to tell you and everybody listening that your catalyst was the only one that drove that carbon-carbon bond formation that I show you on this slide, and it was highly efficient. If you deviate from this catalyst, forget it. You get, in our hands, we got nothing. So thank you, Hugh. So what's on the next slide? Well, this slide tells me that my talk is coming to an end, and I don't know how I did on the time. We were given 20 minutes. I was scared because I counted the slides, and I've got 27 slides, so I tried to be efficient with my discussions of them. But I do want to say that this field of synthesis by way of CH functionalizations is developing beautifully, and you know, in addition to the historically important achievements that I addressed in the course of this brief lecture, you have other ones, other recent achievements that are summarized on this slide. You have syntheses of lithospermic acid by Jin Kwan's laboratory, also by the laboratories of Robert Bergman and John Ellman and their co-workers. These are beautiful undertakings that were highly reliant on CH functionalization events. You have Matt Gaunt's synthesis of resinosine, again featuring CH functionalization reactions. There's the beautiful synthesis of deoxyerythronolide B by Christina White in her lab at the University of University of Illinois, Urbana-Champaign. That was a very bold idea to create the macrocyclic ring in the course of a macro ring forming CH oxidation reaction. The Hongo-Quercetin synthesis from Jin Kwan, also fantastic. Work from China, the synthesis of incarviatone A by Li and Lei, also a very imaginative design. That synthesis was truly highly reliant on CH functionalization reactions. And then you have various projects from the Barron Laboratory. I don't have room to show all of those. The Barron Lab at Scripps is also very active in the area of CH functionalization, CH oxidation, morphing CH bonds into CC bonds, you name it. But the next slide will allow me to express again my gratitude to the center. I'm very proud to be a member of CCHF, and my students are very proud to be members of this center as well. And as we look forward to the future, the groups that are concerned with strategy, so that would include my group, but it includes also Hugh's lab and Brian Stoltz's lab, Richmond Sarpong's lab, and Momo Vasagi's lab. We're all thinking deeply about how we can collaborate on projects in target-directed synthesis, and we're especially interested in research projects that are going to really allow us to push the frontier of strategic innovation forward. And we're keenly interested in strategies that will actually stimulate or drive the development methods development studies and efforts to invent new catalysts to functionalize CH bonds. So on the next slide, I want to thank a few people. I talked about a few projects from my lab. I talked about aspects of the jadophenolide synthesis, which was in the hands of David Seiler and Jeff Midgen. I'm very happy to say that Jeff Midgen will now soon be a new professor at Kent State University in Ohio. The indoxamycin work was sponsored directly by CCHF, and that was taken forward by Aaron Bedell and Graham Hone. Also, Damien Vallette in Hugh's lab. We want to thank Jin Kwan Yu for his expert advice concerning how we could actually achieve the directed palidation of an arene with an in situ Heck reaction. I want to point out, I want to say just briefly a few things about Aaron and Graham. They were the pioneers in my lab with CCHF, and you know, they were great ambassadors for the center, and I deeply appreciate not only the experimental work that they did in my lab, but also you know, their deep commitment to the center and its broad aims. The Maui crystal work, I spoke very briefly about that. There's a lot of work that we did that I didn't talk about. That was in the hands of Jillian Spangler, who's now at Pfizer in La Jolla. Lawrence Herdice, a postdoc from Switzerland, and Michael Smith, who is a key player at the Process Research and Development Group at Bristol Myers Squibb. So I want to thank those students. I want to thank Hugh and all of my colleagues in the center. It's a real honor, a real privilege to be a member of CCHF, and we're extraordinarily grateful for the pervasive impact that it's had on my lab. So with that, I thank all of you for your attention. Thanks.